we draw resonance contributors are drawing all the possible valid Lewis structures with showing all the possible valid location of electrons. That is the resonance contributor. And as I said, we need Lewis structures in order to be able to accurately explain the electron movement from, for example, a nucleophile to an electrophile in a reaction. So, but in reality, the resonance contributors, while they show all the possible location of electrons, they do not show the true location of the electrons that is distributed or that is demonstrated by the resonance hybrid. It's not, I'm trying to change slide. Yes, okay. So we have an analogy for you. Resonance contributors are like unicorns and dragons. They don't actually exist. The actual true demonstration of the placement of electrons is shown by the factual rhinoceros, okay? But the resonance contributors are sufficient to explain electron movement. But you need to know how to interpret and draw them. Okay. So, when do we have delocalized electrons? Cyclooctatetraene. Cyclooctatetraene is not equivalent to benzene with its 6 pi electrons that are delocalized and shared between the carbons. Why is it not equal? The reason that cyclooctatetraene is not the same as benzene is because we do not have p orbital overlap. In order to be stable, cyclooctatetraene is not planar. It has, and so the adjacent pi bonds are perpendicular p orbitals instead of parallel p orbitals. Electrons can only be shared between parallel p orbitals. And so the electrons in cyclooctatetraene cannot be shared. It does not have delocalized electrons because the delocalized electrons are not in the same plane when they are not parallel. Okay, so our delocalized electrons. We have our resonance contributors, unicorn and the dragon, and we can get to the resonance contributors by moving lone pairs and pi electrons that are bonded to atoms which are bonded to an sp2 atom. So, for example, moving the lone pair on this sp3 oxygen into a pi bond, and then, in order not to exceed the octet, moving the pi electrons between the other nitrogen and oxygen to the other oxygen, gives us the second resonance contributor, the dragon. So by moving lone pairs and pi electrons, we should be able to move between unicorn and dragon forms of the resonance contributor. But you should also be able to draw the resonance hybrid, shown below. Note that each of the oxygen is given 2 lone pairs, and that neither of the bonds is a pi bond. Instead, 1 lone pair and 1 pi bond are distributed as these dash marks. And nitrogen is still considered to be positive, and the oxygens are still considered to be, are considered to share the negative charge equally in the actual resonance hybrid. So we have rules for drawing resonance contributors, and we're going to ask you to apply these rules in some exercises. I think that I have an extra exercise that you can do for drawing resonance structures, which I will assign extra credit to. Rules for drawing resonance contributors. Only electrons move. Atoms never move. The electrons that move can only be pi electrons, electrons in pi bonds, or lone pair electrons. Those electrons can move, but sigma electrons can never move. The total number of electrons in the molecule does not change. Each resonance contributor drawn must have the same number of electrons as the former. And electrons always move to an sp2 or an sp atom. sp3 atoms can never accept electrons for resonance structures. Move pi electrons to an sp2 atom. So now we're going through some examples of how to draw resonance structures. We move the pi electrons in the first resonance structure between the two sp2 atoms. One of the carbons will have been part of the original pi bond, and the other carbon should be an sp2 or an sp atom. And you have to remember now what an sp2 atom is. It's an atom that has 3 electron domains. A positively charged carbon has 3 bonds and no lone pairs. And that is 3 electron domains, so it is sp2 hybridized. So we can move pi electrons between 2 sp2 atoms and draw our new resonance contributor. What happens when I move these pi electrons is that carbon 2 loses a bond so that it now only has 3 bonds. So when the pi electrons move, that C2 will only have 3 bonds. And if the carbon only has 3 bonds and no lone pairs, the formal charge will be positive. So you have to make sure that you have the correct charge on all of your atoms. When you have the 2 resonance contributors, that helps you to draw the resonance hybrid. So I know that atoms 2, 3, and 4, because they can share the pi electrons, should have dashed bonds showing that those electrons are shared. Now, what would be incorrect would be that electrons cannot move to an sp3 carbon because an sp3 carbon has an incomplete octet. And so remember what we call the adjacent carbon? It's the allylic carbon. What just happened? Okay, so carbon 4 in the first resonance structure is allylic to the vinyl carbon 3. And in the second structure, the second resonance contributor, C2 is allylic to vinyl carbon 3. So we can move pi electrons if the allylic carbon is sp2 or sp. So those pi electrons can move to an allylic atom that is sp2 or sp hybridized, but they cannot move to an allylic atom that is sp3 hybridized. And that's a rule. And what you need to realize is that if we were to move the electrons, we would actually be exceeding the octet of that carbon atom, because that carbon atom only has sigma bonds. It has 4 sigma bonds, and sigma electrons cannot move. And so if we put pi electrons to that carbon as well, you would exceed the octet. So do not exceed octet. Moving pi electrons continued. So we can move pi electrons to allylic carbons that are sp2. And if we number out the atoms, atoms 2, 3, 4, 5, and 6 are all sp2. So the pi electrons between 2 and 3 are allylic to carbon 4, which is sp2 hybridized. So those electrons can move. The pi electrons between carbon 4 and 5 are allylic to sp2 carbon 6, and so those pi electrons can move. So then, demonstrating the movement of electrons, first, the pi electrons between carbon 4 and 5 are moved, and the new resonance structure is drawn. When we move the pi electrons between 4 and 5, carbon 4 will be left with only 3 bonds, so it is given a positive charge. When we move the pi electrons between 2 and 3 to carbons 3 and 4, then carbon 2 will have a positive charge, as shown here, because then it will only have 3 bonds. So in all, we can draw at least 3 resonance structures for the pi electron movement of these molecules. And the hybrid structure has the partial positive charge and the pi electrons equally distributed between all adjacent sp2 carbons. Shared equally between sp2 in resonance hybrid, as is the formal charge. It's shared equally instead of being placed on only one carbon. And I do want to make one note that if all of the sp2 atoms were not equivalent, then the electrons in the formal charge might not be shared equally. So for example, if instead of having 5 sp2 carbons, we had 4 sp2 carbons and an sp2 oxygen, then the carbons would share the positive charge equally, but the oxygen is more electronegative, and so it would not share that positive charge equally. Okay. Moving lone pair electrons to an sp2 carbon. Lone pair electrons can move from an sp3 atom to an sp2 carbon as long as there is a pi bond that can move. So, and pi bonds can only be moved to sp2 atoms. So in the original structure, we have an sp2 oxygen, an sp2 carbon, and an sp3 nitrogen. The lone pair on the sp3 nitrogen can be moved to the sp2 carbon. So again, we can only move the electrons to sp2 or sp hybridized atoms. If you move the lone pair to the sp2 carbon, in order to prevent exceeding the octet, the pi electrons of the sp2 between the sp2 carbon and the sp2 oxygen must be moved to the sp2 oxygen, which will make it sp3 hybridized. So in the resonance contributor, we'll now have an sp3 hybridized oxygen with lone pairs, the sp2 hybridized carbon, and an sp2 hybridized nitrogen. And the electrons then can be moved back from the sp3 carbon lone pair can be moved back into a pi bond, and the pi bond between carbon and nitrogen, those electrons can be moved back into a lone pair on the nitrogen, giving us the original structure. And so we can show this equal distribution of electrons between these 3 atoms using a resonance hybrid. Resonance hybrid shown here. But if there is an sp3 atom between an sp3 lone pair and an sp2 carbon, then the electrons cannot be moved. So we cannot move lone pair to an sp3 atom. Moving pi electrons to an sp carbon. When we move one pi bond to an sp carbon, we break the bond between the pi between carbon and hydrogen. So now the C1, well, I'm going to name it from this, number it from the other side, from the nitrile side, just to stick with our numbering rules. 1, 2, 3. Okay, so carbon 3, when we move this pi bond as shown, has only 3 bonds, so it will become positive. Once we move the pi bond to between carbon 1 and 2, carbon 1 will exceed an octet unless we move the pi bond between carbon and nitrogen to the nitrogen. So we have an sp3 carbon at sp2, so hybridization sp2, sp2, sp, and sp. And when we draw our resonance contributor shown by the arrows given, we get sp2, sp2, sp, and sp2 from the way that the electrons moved. So the positively charged carbon 3, which now only has one single bond and one empty p orbital and single bonds to hydrogen, is sp2 hybridized. Our carbon 2, which had a pi bond that moved to the other side, is still sp2 hybridized. Our cyanonitrile carbon, carbon 1, is sp hybridized. It still has a total of 4 bonds, and it still has a total of 2 pi bonds, but the pi bonds are distributed differently. And then between the carbon and nitrogen, the pi bond which we moved to a lone pair, none of the atoms is exceeding an octet, and we only moved pi electrons in lone pairs. And the formal negative charge is given to the more electronegative atom, and the formal positive charge is shown on the carbon. In the resonance hybrid, you have to show the polarity of the atom, explaining the distribution of the charges in partial signs, showing partial negative on nitrogen and a partial positive at the carbon. Okay, practice problem. I'll come back to that. Okay, so let's look at this practice problem. And I'll stay in this view because it's just easier for me to manipulate and draw in this view. Which of the following compounds have delocalized electrons? So this is all going to hitch on, do we have pi bonds or lone pairs that can move to an sp2 atom? So you have to know and be able to recognize quickly, snap your fingers, where your sp3 atoms are. CH2 groups, if they're inside an internal CH2 group that's not the last carbon in the chain, is always going to be sp3. So here we have an sp3 atom smack dab in the middle of our two sp2s. So we cannot move electrons because of this. No. All right, so then look at the next one. We have 2 pi bonds and a positive charge. And let's check, do we have any sp3 atoms in here? We got sp2, 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 and sp2. So yes, I can move the electrons. All right, so this lone pair, can it move? Let's see. We got sp3 and sp3 on either side of the lone pair, so no for the lone pair. What about the pi electrons? Well, they're already between 2 sp2 carbons, but they can't move to another sp2, so no, because they're next to an sp3. Aw. All right, no. Just trying to move this green. All right, so then looking at the nitrogen, this molecule, the only atom that is sp3 hybridized is the atom with the lone pairs, and all of the carbons are sp2 hybridized. This is just another image of the same thing. So yes, we can move the sp3 electrons to the sp2 atom, and yes, we can move sp2 pi electrons to other sp2 atoms. These electrons can move. They are delocalized. All right, now we have a lone pair next to an sp2 carbon, so yes, we can move this lone pair. And we have pi electrons on 2 sp2 carbons, but the pi electrons cannot move. They are localized. Because if I were to move the pi electrons to the nitrogen, that would be moving pi electrons to an sp3 atom, which isn't allowed. But what can happen, the way that you can draw the resonance structure, is well, let me draw a different sideways benzene ring. Smaller arrow. Move the ring over. Whoops. Now I can add my bond to nitrogen. So what I'm going to do, the resonance structure is going to have the lone pair from nitrogen being moved to between the nitrogen and the sp2 carbon. So we have a new pi bond. And because we can't exceed the octet, what happens to the other lone pair is that it becomes individually drawn on the sp2 carbon on the far sp2 carbon. So if we number the nitrogen as 1 and then 2 and then 3 assigned to the pi carbons in the original structure, now we have a pi carbon between N at 1 and C at 2, but a lone pair on the carbon at position 3. And so these are two valid resonance structures. So the lone pair on nitrogen can move, and the only way that we can move the pi electrons is to an individual carbon. As shown. Okay. So next we have sp3 with lone pairs, followed by an sp3, followed by an sp2. So we can only move lone pairs if we can move them to an sp3 atom, and we can only move pi electrons. We can only move one lone pairs if we can move it to an sp2 atom. So because that would be moving to sp2, it's not allowed. So cross that out. And then we can only move pi electrons if we're moving to sp2, so that's not allowed, and we can cross that out. So we can say that no, those electrons cannot move. It wasn't done. Okay. Number 7, I can already tell you that we have an sp3 between our lone pair and our pi electrons, so no, we can't move those electrons. And then I think there's another example. So here we have another example that said draw the resonance contributors for the compounds that have delocalized electrons. And you can think of drawing a resonance contributor is similar to having to draw the product of a reaction. What you're going to do is to show the electron flow. So if I move these pi electrons here and these pi electrons here, then that gives me my new resonance contributor. And from showing that movement, I can number my carbons and parse down how I'm going to draw my resonance contributor. So I can tell myself that I'm taking the pi electrons from 2 and 3 and moving them to 3 and 4. There's where they move to, between 3 and 4. When I move the electrons between 2 and 3 to 3 and 4, 2 becomes positive. I also show the pi electrons from 4 to 5 moving to from 5 to 6. So the pi electrons, so I have pi electrons from 5 to 6 in my resonance contributor. So if you take the original structure they give you and show the electrons moving by arrows and then number the molecule, you should be able to draw the product of that electron movement. Okay, so another example. Okay, so firstly, I'll show you one without electrons drawn in. I'm just going to put the basic ring there and then fill in the electrons based on how I move them. Okay, so I'm going to move the lone pair from the nitrogen to a pi bond between carbon and nitrogen, and the carbon-carbon pi bond I'll place as a lone pair on a specific carbon atom. Let's go the other way. Those arrows. Move it here and place this here as a lone pair. Then I have to draw the product of that reaction. I have to draw that I still have this lone pair between, or this pi bond. If I number nitrogen is 1, 2, 3, 4, 5. Between 4 and 5, I still have the pi bond. I didn't touch those with my electron arrows. But the lone pair, I moved to a pi bond between the nitrogen at 1 and the carbon at 2. And now nitrogen is going to have a positive charge because it has 4 bonds and no lone pairs. And then the pi bond between carbon 2 and carbon 3, I put as a lone pair on carbon 3. Now let's show the electron movement for this resonance structure. So next, I can still draw more resonance structures. I can move this lone pair on carbon 3 to a pi bond between 3 and 4. When I do that, I have to move the lone pair on between 4 and 5 to or the pi bond between 4 and 5 to a lone pair on 5. So then we draw the product of that. And we show that the lone pair on 3 is now a pi bond between 3 and 4. And the pi bond at 4 is now a lone pair on 5. And we still have the pi bond between nitrogen and carbon 2. So then in the final resonance contributor, you should be able to move the electrons in such a way that you obtain the original molecule. So let me show you this. If I take the lone pair at carbon 5, and it should have a negative charge when it has a lone pair. If I take the lone pair at carbon 5 and I move it to a pi bond between 5 and nitrogen at 1, then I have to move the pi bond between the nitrogen at 1 and carbon 2. And so I'm just going to go ahead and draw that moving to a pi bond between carbon 2 and 3. And then I'll draw the pi bond between 3 and 4, moving to a pi bond between 4 and 5. And when I draw those 3 arrows, that actually takes me back to the original structure. And that's what I'm showing with the arrow going from the last ring to the first ring underneath. Okay? And then drawing the resonance contributors for the 6-membered ring. you should be able to do that. We showed it on the previous page. So what I would do is I would move these electrons into a pi bond and these pi electrons into a single pair. And then draw the resonance structure that I have indicated by my electron flow arrows. So pi bond between N and C and a lone pair at the C. And that takes us through this example, and we've drawn all the resonance contributors. We have some more examples on the next slide, but I should probably erase it. All right, so looking at the next slide, draw resonance contributors that have delocalized electrons. What I've actually done here is not just draw the resonance contributors. For 2 and 4, I drew the resonance hybrids, showing that there is complete electron sharing across all of the sp2 atoms. So notice that in the resonance hybrid, you show dots across all of the atoms that are sharing electrons. Same thing for the resonance hybrid of 4, showing the electrons being shared across all of the atoms, which can also be demonstrated with a circle. And then in the last structure, drawing the resonance contributors, and then drawing the resonance hybrid, which is here. So these are the resonance hybrids. All right, so let's start a new video, and then we can pick back up. Actually, one more thing. Looking at the next slide, I might just go ahead and cover this. One of the things that we'll cover in biochem is that we have delocalized electrons and resonance structures for biological molecules. Amino acids have delocalized electrons, the nitrogens have lone pairs, and the oxygens have pi bonds. These atoms share electrons between them. So carbon, oxygen, and nitrogen, in each of these cases, give me the pen. It says it's on. It says I'm picking red. Why isn't it working? Okay. So these 3 electrons are sharing the pi and the lone pair electrons of nitrogen and carbon and oxygen. So for every single amino acid, we have delocalized electrons, and that has a significant biological effect. It's very important to the structure of the proteins. The fact that we don't have that we have a partial pi bond but not a full pi bond. It makes amino acids able to form very specific structures in protein structures. And these are structures that you've learned about. Seriously? This is so weird. I think I need to restart my computer. Laser pointer. Okay. We have alpha helices and beta barrels that are formed because of the resonance structure of the amide, carbonyl, and nitrogen lone pair. So reviewing the stability and another biological molecule that has resonance contributors, DNA. But we'll talk about that later. So stability of resonance contributors must have features that decrease predicted stability. We're going to pick up with these rules, and we're going to now be able to, what we're going to do is we're going to use these rules to rate good resonance structure, poor resonance structure, and identify which resonance structure is more close to the resonance hybrid.